Okay, so let's continue with the non-stationary time series analysis with manifold learning techniques. And in this lecture, I want to detour a bit to talk a bit about unsupervised manifold learning and at least to have some very basic ideas of how to apply diffusion map to general problems. So the focus will be clustering, the clustering problem. And the goal of clustering is the following. Usually on the left-hand side, I give you point clouds, and usually you don't know what's going on or what's the relationship. And you basically have no idea. But now, I want to convert something that we have no idea into something that is smart. So that we can say, hey, just from the data, we have actually some kind of patterns. And this kind of pattern is actually quite easy by our eyes, isn't it? If you just pay attention, I tell you, oh, there are 3 clusters. Maybe you can easily tell me there will be 3 clusters. Why? Because you have got some trainings, you have got some life experience, and so on. Many, many reasons. Or you may say, oh, there are some feelings, and so on. No matter what. Then how to quantify it? How to make it automatic? So that we can make computer to do this clustering business for us. So a formal description, mathematical description of clustering is the following. Usually I give you a set of objects, n objects, and certainly there will be some metric you know how to compare pairs of points. And you want to construct k disjoint sets that partitioning the data set X. Okay, but we need to put some constraint, otherwise the partition can be random, right? And the constraint says the following. The objects inside each cluster are more similar than objects from different clusters. That would be the constraint. So far it's still a bit vague, but you can see the idea. The idea is we have some kind of notion about comparison, and when we do the comparison, we want to partition the data set into disjoint subsets so that all objects inside each cluster are more similar compared with different clusters. Very simple. Mathematically, that is what you can write. You can define some kind of within cluster scaters, and this scatter is defined using, for example, L2 distance as the metric. You compare all pairwise distance within a cluster, and you have mean, and you sum everything. That is called within cluster scatter. And actually, this quantity is part of the total scatter of the data set X. That is, you calculate all pairwise distances inside the data set, and it can be written as the within cluster scatter and the within in between different cluster scatter. And so you see, this is what we have interest. We want to somehow minimize this distance, and simultaneously we want to maximize this quantity, and so on. So there are several things you can consider. In the end of the day, we have some very basic property of scatter, saying that suppose you have mu k, and this mu k is actually the mean of each cluster. Mu k is the mean of the kth cluster. Then the within cluster scatter is nothing but the distance in between each point and its associated center. Okay, so the algorithm becomes very simple. We want to minimize the within cluster scatter as the loss function, and how to minimize it, we try to find the cluster and the centers so that this within cluster scatter is minimized. And to minimize this functional, the algorithm is called k-mean, and this k-mean is an iterative algorithm which is summarized here, but I will use a picture in the next slide to show you, describe it step by step, which is very simple. What you do is you find the initial seed, and once you find the initial seed, okay, for example, these 2 points, and then you assign all the points to the closest seed. For example, in the very beginning, you cluster all the points into 2 clusters. Okay, and after round 1, you find all these both clusters, and you evaluate the mean. Once you evaluate the mean, then you reassign the weight. You reassign the points to the center, and you iterate, and finally you get the clusters, and also the means of each cluster. So the idea is very simple. You just randomly assign seeds, and assign all the points to the seed. You randomly assign the centers. Okay, assume these 2 are the centers, and you assign all the points to the associated center. You update the center, and after updating the center, you reassign all the points to the center, and you iterate it until it converges. Okay, so this is a simple result. Once you apply this k-means, certainly you need to know k, how many k, and there are some algorithms that can help you to determine k, which you can find online and so on, which I will not go into details. Okay, and that is the basic k-mean algorithm. And there are some applications and some limitations. The first application is compression, or called vector quantization. And this is in the image processing society, it's called Lloyd's algorithm, or this LBG algorithm. And what you do is very simple. I give you an image, and you truncate it into pieces. Okay, each piece truncated into pieces. Each piece can be viewed as a point in high-dimensional space. And then you run k-means. And once you run k-mean, you somehow divide the domain into pieces. And then for all the points or all the patches inside one cluster, you replace it by the center so that you compress the image. So that is called vector quantization. And this is the result, an example. Suppose I give you the original image, and you construct a 2x2 non-overlapping patches. Okay, you repeat it. Okay, so each patch in the end will be 12-dimensional vector because it contains 2x2 patches, and there's RGB 3-dimensional. Okay, so each patch is a 12-dimensional vector, and now in the 12-dimensional Euclidean space, you get that many 230,000 vectors. And what you do is, let's run k-mean. Suppose k is 32, then you classify each patch into 30 clusters. And over each cluster, you use the center to replace each patch. And this is the result when k is 32. So technically, you get a lot of compression, but if you pay attention to both, you see most information details are preserved. And even if you take k is 8 or k is 2, you see quite a lot of information is still preserved. So that is one application of k-mean idea in image compression. But as I mentioned, it is not everything, it has limitations. For example, I give a data set of 2 circles. And if I ask you how many clusters are there and how to do clustering, you may tell me there are 2 clusters, right? 2 circles. But if you run k-mean algorithm, you see this is the result. The red one and the black one, two clusters. Why? Because K-mean algorithm respects the metric you use. And the metric we use here is actually the global Euclidean distance. So it cannot tell you any intrinsic nonlinear geometry inside the Euclidean space. You cannot tell it. So we need something. And the basic idea is called spectral clustering, which is a very popular algorithm back in 2000. There was a paper by Xu and Malik. I should cite it here, but I forgot. But then Xu and Malik's paper back in 2000 was cited by, I don't know, hundreds of thousands, many thousand times, which was the foundation of this algorithm. And the basic idea is, let's run some spectral embedding or whatever embedding you like to emphasize the intrinsic geometry before you run K-means. So you run spectral embedding or like diffusion map, and after you do the embedding, you run K-means, and then you get a classification. That is called spectral clustering. So spectral clustering is spectral embedding plus K-mean, and this is the result. It gives you a good result already. Okay. For example, here 3 clusters, quite nice. Here 3 clusters, quite nice. But it still has some limitations. For example, in this example, 3 clusters, but it fails. And here, if you choose the bandwidth in the wrong way, then it also fails, and it fails. Although our eyes are very good, we can see into the intrinsic geometry immediately, but the algorithm cannot, the spectral clustering cannot. So what people considered was called self-tuned spectral clustering. This is the paper. The algorithm was based on, well, I forgot to cite it again, which is published in 2006 by a group from Caltech. So they take the density into account, called self-tuned spectral clustering. The basic idea is very simple. They determine the bandwidth using the local density of the data, and they use this kind of density-aware bandwidth to construct the graph Laplacian and the spectral embedding before the K-means. So the result turns out to be quite nice. So you can see almost everything can be well clustered. So yeah, the algorithm is actually very simple. So you have to define Wij. What you do is you construct Wij. What you do is you construct xi minus xj squared, but you have sigma I, sigma j, and the sigma I is the distance. I remember the xi7 minus xi equal to distance. This one means the 7th nearest neighbor of xi. So that is what you do. So you can see that by choosing the bandwidth in this way, if at some point the data sampling is very dense, then sigma I will be small. But if over xi the data is very sparse, then sigma I will be big. So this is how the density information is taken into account to determine affinity. So this can be viewed as an affinity design or metric design technique, which we will come back to discuss when we talk about manifold learning later, which is a very good technique, very good trick to handle very non-uniform dense sampling data set. Yes, that's it.